Volcanic ash consists of fragments of pulverized rock, minerals and volcanic glass, created during volcanic eruptions and measuring less than 2 mm in diameter. The term volcanic ash is also often loosely used to refer to all explosive eruption products, including particles larger than 2 mm. Volcanic ash is formed during explosive volcanic eruptions when dissolved gases and magma expand and escape violently into the atmosphere. The force of the escaping gas shatters the magma and propels it into the atmosphere where it solidifies into fragments of volcanic rock and glass. Ash is also produced when magma comes into contact with water during phreatomagmatic eruptions, causing the water to explosively flash to steam leading to shattering of magma. Once in the air, ash is transported by wind up to thousands of kilometers away. Due to its wide dispersal, ash can have a number of impacts on society, including human and animal health, disruption to aviation, disruption to critical infrastructure, primary industries, buildings and structures. Formation. Volcanic ash is formed during explosive volcanic eruptions, phreatomagmatic eruptions and during transport in pyroclastic density currents. Explosive eruptions occur when magma decompresses as it rises, allowing dissolved volatiles to exhalve into gas bubbles. As more bubbles nucleate, a foam is produced, which decreases the density of the magma, accelerating it up the conduit. Fragmentation occurs when bubbles occupy 70–80% of the erupting mixture. When fragmentation occurs, violently expanding bubbles tear the magma apart into fragments which are ejected into the atmosphere where they solidify into ash particles. Fragmentation is a very efficient process of ash formation and is capable of generating very fine ash even without the addition of water. Volcanic ash is also produced during phreatomagmatic eruptions. During these eruptions, fragmentation occurs when magma comes into contact with bodies of water, groundwater, snow or ice. As the magma, which is significantly hotter than the boiling point of water, comes into contact with water, an insulating vapor film forms. Eventually this vapor film will collapse, leading to direct coupling of the cold water and hot magma. This increases the heat transfer, which leads to the rapid expansion of water and fragmentation of the magma into small particles which are subsequently ejected from the volcanic vent. Fragmentation causes an increase in contact area between magma and water, creating a feedback mechanism, leading to further fragmentation and production of fine ash particles. Pyroclastic density currents can also produce ash particles. These are typically produced by lava dome collapse or collapse of the eruption column. Within pyroclastic density currents, particle abrasion occurs as particles interact with each other, resulting in a reduction in grain size and production of fine-grained ash particles. In addition, ash can be produced during secondary fragmentation of pumice fragments, due to the conservation of heat within the flow. These processes produce large quantities of very fine-grained ash, which is removed from pyroclastic density currents in bright ash plumes. Physical and chemical characteristics of volcanic ash are primarily controlled by the style of volcanic eruption. Volcanoes display a range of eruption styles which are controlled by magma chemistry, crystal content, temperature and dissolved gases of the erupting magma, and can be classified using the Volcanic Explosivity Index. Effusive eruptions of basaltic composition produce 109 m3 of ejecta into the atmosphere. Another parameter controlling the amount of ash produced is the duration of the eruption. The longer the eruption is sustained, the more ash will be produced. For example, the second phase of the 2010 eruptions of Ujjayi, a larger paragraph Kull, was classified as VEI4 despite a modest 8 km high eruption column, but the eruption continued for a month, which allowed a large volume of ash to be ejected into the atmosphere. Properties. Chemical. The types of minerals present in volcanic ash are dependent on the chemistry of the magma from which it erupted. Considering that the most abundant elements found in magma are silica and oxygen, the various types of magma produced during volcanic eruptions are most commonly explained in terms of their silica content. Low-energy eruptions of basalt produce a characteristically dark-colored ash containing 45–55% silica that is generally rich in iron and magnesium. The most explosive rhyolite eruptions produce a felsic ash that is high in silica, while other types of ash with an intermediate composition have a silica content between 55 to 69%. The principal gases released during volcanic activity are water, carbon dioxide, sulfur dioxide, hydrogen, hydrogen sulfide, carbon monoxide and hydrogen chloride. These sulfur and halogen gases and metals are removed from the atmosphere by processes of chemical reaction, dry and wet deposition, and by adsorption onto the surface of volcanic ash. It has long been recognized that a range of sulfate and halide compounds are readily mobilized from fresh volcanic ash. It is considered most likely that these salts are formed as a consequence of rapid acid dissolution of ash particles within eruption plumes, which is thought to supply the cations involved in the deposition of sulfate and halide salts. While some 55 ionic species have been reported in fresh ash leachates, the most abundant species usually found are the cations Na+, K+, Ca2+, and Mg2+, and the anions Cla, Fa and SO42A. Molar ratios between ions present in leachates suggest that in many cases these elements are present as simple salts such as NaCl and CaSO4. In a sequential leaching experiment on ash from the 1980 eruption of Mount St. Helens, chloride salts were found to be the most readily soluble, followed by sulfate salts. Fluoride compounds are in general only sparingly soluble, with the exception of fluoride salts of alkali metals and compounds such as calcium hexafluorosilicate. The pH of fresh ash leachates is highly variable, depending on the presence of an acidic gas condensate on the ash surface. The crystalline solid structure of the salts act more as an insulator than a conductor. However, once the salts are dissolved into a solution by a source of moisture, the ash may become corrosive and electrically conductive. A recent study has shown that the electrical conductivity of volcanic ash increases with increasing moisture content, increasing soluble salt content, and increasing compaction. The ability of volcanic ash to conduct electric current has significant implications for electric power supply systems. Physical components. Volcanic ash particles erupted during magmatic eruptions are made up of various fractions of vitric, crystalline or lithic particles. Ash produced during low-viscosity magmatic eruptions produce a range of different pyroclasts dependent on the eruptive process. For example, ash collected from Hawaiian lava fountains consists of siderumlan pyroclasts which contain rare microliths and phenocrysts. Slightly more viscous eruptions of basalt form a variety of pyroclasts from irregular siderumlan droplets to blocky tachylite. In contrast, most high silica ash consists of pulverized products of pumice, individual phenocrysts and some lithic fragments. Ash generated during phreatic eruptio, ENS primarily consists of hydrothermally altered lithic and mineral fragments, commonly in a clay matrix. Particle surfaces are often coated with aggregates of xylite crystals or clay and only relic textures remain to identify pyroclast types. Morphology. The morphology of volcanic ash is controlled by a plethora of different eruption and kinematic processes. Eruptions of low-viscosity magmas typically form droplet-shaped particles. This droplet shape is, in part, controlled by surface tension, acceleration of the droplets after they leave the vent, and air friction. Shapes range from perfect spheres to a variety of twisted, elongate droplets with smooth, fluidal surfaces. The morphology of ash from eruptions of high-viscosity magmas is mostly dependent on the shape of vesicles in the rising magma before disintegration. Vesicles are formed by the expansion of magmatic gas before the magma has solidified. Ash particles can have varying degrees of vesicularity, and vesicular particles can have extremely high surface area to volume ratios. Concavities, troughs, and tubes observed on grain surfaces are the result of broken vesicle walls. Vitric ash particles from high-viscosity magma eruptions are typically angular, vesicular pumiceous fragments or thin vesicle wall fragments, while lithic fragments in volcanic ash are typically ecant, or angular to subrounded. Lithic morphology in ash is generally controlled by the mechanical properties of the wall rock broken up by spalling or explosive expansion of gases in the magma as it reaches the surface. The morphology of ash particles from phreatomagmatic eruptions is controlled by stresses within the chilled magma which result in fragmentation of the glass to form small blocky or pyramidal glass ash particles. Vesicle shape and density play only a minor role in the determination of grain shape in phreatomagmatic eruptions. In this sort of eruption, the rising magma is quickly cooled on contact with ground or surface water. Stresses within the quenched magma cause fragmentation into 5 dominant pyroclast shape types: blocky and decant, vesicular and irregular with smooth surfaces, moss-like and convoluted, spherical or drop-like, and plate-like. Density: the density of individual particles varies with different eruptions. The density of volcanic ash varies between 700 euro 1200 kg per meter 3 for pumice, 2350 euro 2450 kg per meter 3 for glass shards, 2700 euro 3300 kg per meter 3 for crystals, and 2600 euro 3200 kg per meter 3 for lithic particles. Since coarser and denser particles are deposited close to source, fine glass and pumice shards are relatively enriched in ash fall deposits at distal locations. The high density and hardness together with a high degree of angularity, make some types of volcanic ash very abrasive. Grain size: volcanic ash consists of particles with diameters 2 mm are classified as lapilli, and can be as fine as 1/4 m. The overall grain size distribution of ash can vary greatly with different magma compositions. Few attempts have been made to correlate the grain size characteristics of a deposit with those of the event which produced it, though some predictions can be made. Rhyolitic magmas generally produce finer-grained material compared to basaltic magmas, due to the higher viscosity and therefore explosivity. The proportions of fine ash are higher for silicic explosive eruptions, probably because vesicle size in the pre-eruptive magma is smaller than those in mafic magmas. There is good evidence that pyroclastic flows produce high proportions of fine ash by comminution, and it is likely that this process also occurs inside volcanic conduits and would be most efficient when the magma fragmentation surface is well below the summit crater. Dispersal: ash particles are incorporated into eruption columns as they are ejected from the vent at high velocity. The initial momentum from the eruption propels the column upwards. As air is drawn into the column, the bulk density decreases and it starts to rise buoyantly into the atmosphere. At a point where the bulk density of the column is the same as the surrounding atmosphere, the column will cease rising and start moving laterally. Lateral dispersion is controlled by prevailing winds, and the ash may be deposited hundreds to thousands of kilometers from the volcano, depending on eruption column height, particle size of the ash and climatic conditions. Ash fallout occurs immediately after the eruption and is controlled by particle density. Initially, coarse particles fall out close to source. This is followed by fallout of accretionary lapilli, which is the result of particle agglomeration within the column. Ash fallout is less concentrated during the final stages as the column moves downwind. This results in an ash fall deposit which generally decreases in thickness and grain size exponentially with increasing distance from the volcano. Fine ash particles may remain in the atmosphere for days to weeks and be dispersed by high-altitude winds. These particles can impact on the aviation industry and, combined with gas particles, can affect global climate. Volcanic ash plumes can form above pyroclastic density currents. These are called co-inumbrite plumes. As pyroclastic density currents travel away from the volcano, smaller particles are removed from the flow by elidriation and form a less dense zone overlying the main flow. This zone then entrains the surrounding air and a buoyant co-inumbrite plume is formed. These plumes tend to have higher concentrations of fine ash particles compared to magmatic eruption plumes due to the abrasion within the pyroclastic density current. Impacts: Introduction Population growth has caused the progressive encroachment of urban development into higher-risk areas, closer to volcanic centers, increasing the human exposure to volcanic ash fall events. Infrastructure is critical to supporting modern societies, particularly in urban areas, where high population densities create high demand for services. These infrastructure networks and systems support urban living, and provide lifeline services upon which we depend for our health, education, transport and social networking. Infrastructure networks and services support a variety of facilities across a broad range of sectors. Volcanic ash fall events can disrupt and/or damage the infrastructure upon which society depends. Several recent eruptions have illustrated the vulnerability of urban areas that received only a few millimeters or centimeters of volcanic ash. This has been sufficient to cause disruption of transportation, electricity, water, sewage and stormwater systems. Costs have been incurred from business disruption, replacement of damaged parts and insured losses. Ashfall impacts on critical infrastructure can also cause multiple knock-on effects, which may disrupt many different sectors and services. Volcanic ash fall is physically, socially and economically disruptive. Volcanic ash can affect both proximal areas and areas many hundreds of kilometers from the source, and causes disruptions and losses in a wide variety of different infrastructure sectors. Impacts are dependent on ash fall thickness, the duration of the ash fall, the grain size and chemistry of the ash, whether the ash is wet or dry, and any preparedness, management and prevention measures employed to reduce effects from the ash fall. Different sectors of infrastructure and society are affected in different ways and are vulnerable to a range of impacts or consequences. These are discussed in the following sections. Infrastructure sectors Electricity. Volcanic ash can cause disruption to electric power supply systems at all levels of power generation, transformation, transmission and distribution. There are four main impacts arising from ash contamination of apparatus used in the power delivery process. Wet deposits of ash on high-voltage insulators can initiate a leakage current which, if sufficient current is achieved, can cause a flashover, a unregistered trademark. If the resulting short-circuit current is high enough to trip the circuit breaker, then disruption of service will occur. Ash-induced flashover across transformer insulation can burn, etch or crack the insulation irreparably and will likely result in the disruption of power supply. Volcanic ash can erode, pit and scour metallic apparatus, particularly moving parts such as water and wind turbines and cooling fans on transformers or thermal power plants. The high bulk density of some ash deposits can cause line breakage and damage to steel towers and wooden poles due to ash loading. This is most hazardous when the ash and or the lines and structures are wet and there has been a per-mil-10 of ash fall. Fine-grained ash of modern large jet engines. The degree of impact depends upon the concentration of ash in the plume, the length of time the aircraft spends within the plume and the actions taken by the pilots. Critically, melting of ash, particularly volcanic glass, can result in accumulation of resolidified ash on turbine nozzle guide vanes, resulting in compressor stall and complete loss of engine thrust. The standard procedure of the engine control system when it detects a possible stall is to increase power, which would exacerbate the problem. It is recommended that pilots reduce engine power and quickly exit the cloud by performing a descending 180-degree turn. Volcanic gases, which are present within ash clouds, can also cause damage to engines and acrylic windshields, although this damage may not surface for many years. Occurrence There are many instances of damage to jet aircraft as a result of an ash encounter. On June 24, 1982, a British Airways Boeing 747-236B flew through the ash cloud from the eruption of Mount Galunggung, Indonesia, resulting in the failure of all four engines. The plane descended 24,000 feet in 16 minutes before the engines restarted, allowing the aircraft to make an emergency landing. On December 15, 1989, a KLM Boeing 747-400 also lost power to all four engines after flying into an ash cloud from Mount Redoubt, Alaska. After dropping 14,700 feet in 4 minutes, the engines were started just 2 minutes before impact. Total damage was $80 million and it took 3 months' work to repair the plane. In the 1990s, a further $100 million of damage was sustained by commercial aircraft as a consequence of the 1991 eruption of Mount Pinatubo in the Philippines. In April 2010, airspace all over Europe was affected, with many flights cancelled, which was unprecedented due to the presence of volcanic ash in the upper atmosphere from the eruption of the Icelandic volcano Uja Larger Paragraph Kull. On April 15, 2010, the Finnish Air Force halted training flights when damage was found from volcanic dust ingestion by the engines of one of its Boeing F-18 Hornet fighters. On April 22, 2010, UK RAF Typhoon training flights were also temporarily suspended after deposits of volcanic ash were found in a jet's engines. In June 2011, there were similar closures of airspace in Chile, Argentina, Brazil, Australia and New Zealand, following the eruption of Puhu Corda Cubed en Core, Chile. Detection equals. Volcanic ash clouds are very difficult to detect from aircraft as no onboard cockpit instruments exist to detect them. However, a new system called Airborne Volcanic Object Infrared Detector has recently been developed by Mechanical Aviation, a daughter company of the Norwegian Institute for Air Research, which will allow pilots to detect ash plumes up to 100 kilometers ahead and fly safely around them. The system uses two fast sampling infrared cameras, mounted on a forward-facing surface, that are tuned to detect volcanic ash. This system can detect ash concentrations of 50 mg per meter 3, giving pilots approximately 7 €10 minutes warning. The camera is currently being tested by EasyJet Airline Company. In addition, ground and satellite-based imagery, radar, and LiDAR can be used to detect ash clouds. This information is passed between meteorological agencies, volcanic observatories and airline companies through volcanic ash advisory centers. There is one VAAC for each of the 9 regions of the world. VAACs can issue advisories describing the current and future extent of the ash cloud. Airport systems volcanic ash not only affects in-flight operations but can affect ground-based airport operations as well. Small accumulations of ash can reduce visibility, create slippery runways and taxiways, infiltrate communication and electrical systems, interrupt ground services, damage buildings and parked aircraft. Ash accumulation of more than a few millimeters requires removal before airports can resume full operations. Ash does not disappear and must be disposed of in a manner that prevents it from being remobilized by wind and aircraft. Land transport. Ash may disrupt transportation systems over large areas for hours to days, including roads and vehicles, railways and ports and shipping. Falling ash will reduce the visibility, which can make driving difficult and dangerous. In addition, fast-traveling cars will stir up ash, creating billowing clouds which perpetuate ongoing visibility hazards. Ash accumulations will decrease traction, especially when wet, and cover road markings. Fine-grained ash can infiltrate openings in cars and abrade most surfaces, especially between moving parts. Air and oil filters will become blocked, requiring frequent replacement. Rail transport is less vulnerable, with disruptions mainly caused by reduction in visibility. Marine transport can also be impacted by volcanic ash. Ashfall will block air and oil filters and abrade any moving parts if ingested into engines. Navigation will be impacted by a reduction in visibility during ashfall. Vesiculated ash will float on the water surface in a pumice rafts, a unregistered trademark which can clog water intakes quickly, leading to overheating of machinery. Communications, telecommunication and broadcast networks can be affected by volcanic ash in the following ways: attenuation and reduction of signal strength, damage to equipment, and overloading of network through user demand. Signal attenuation due to volcanic ash is not well documented. However, there have been reports of disrupted communications following the 1969 Surtsey eruption and 1991 Mount Pinatubo eruption. Research by the New Zealand-based Auckland Engineering Lifelines Group determined theoretically that impacts on telecommunications signals from ash would be limited to low-frequency services such as satellite communication. Signal interference may also be caused by lightning, as this is frequently generated within volcanic eruption plumes. Telecommunication equipment may become damaged due to direct ash fall. Most modern equipment requires constant cooling from air conditioning units. These are susceptible to blockage by ash, which reduces their cooling efficiency. Heavy ash falls may cause telecommunication lines, masts, cables, aerials, antennae dishes and towers to collapse due to ash loading. Moist ash may also cause accelerated corrosion of metal components. Reports from recent eruptions suggest that the largest disruption to communication networks is overloading due to high user demand. This is common of many natural disasters. Computers may be impacted by volcanic ash, with their functionality and usability decreasing during ashfall, but it is unlikely they will completely fail. The most vulnerable components are the mechanical components, such as cooling fans, CD drives, keyboard, mice and touch pads. These components can become jammed with fine-grained ash, causing them to cease working. However, most can be restored to working order by cleaning with compressed air. Moist ash may cause electrical short circuits within desktop computers. However, will not affect laptop computers. Buildings and structures. Damage to buildings and structures can range from complete or partial roof collapse to less catastrophic damage of exterior and internal materials. Impacts depend on the thickness of ash, whether it is wet or dry, the roof and building design and how much ash gets inside a building. The specific weight of ash can vary significantly and rain can increase this by 50 to 100%. Problems associated with ash loading are similar to that of snow. However, ash is more severe as 1, the load from ash is generally much greater, 2, ash does not melt and 3, ash can clog and damage gutters, especially after rainfall. Impacts for ash loading depend on building design and construction, including roof slope, construction materials, roof span and support system, and age and maintenance of the building. Generally, flat roofs are more susceptible to damage and collapse than steeply pitched roofs. Roofs made of smooth materials are more likely to shed ash than roofs made with rough materials. Roof collapse can lead to widespread injuries and deaths and property damage. For example, the collapse of roofs from ash during the 15 June 1991 Mount Pinatubo eruption killed about 300 people. Human and animal health. Ash particles of less than 10 micrometer diameter suspended in the air are known to be inhalable, and people exposed to ash falls have experienced respiratory discomfort, breathing difficulty, eye and skin irritation, and nose and throat symptoms. Most of these effects are short-term and are not considered to pose a significant health risk to those without pre-existing respiratory conditions. The health effects of volcanic ash depend on the grain size, mineralogical composition and chemical coatings on the surface of the ash particles. Additional factors related to potential respiratory symptoms are the frequency and duration of exposure, the concentration of ash in the air and the respirable ash fraction. The proportion of ash with less than 10 micrometer diameter, known as PM10. The social context may also be important. Chronic health effects from volcanic ash fall are possible, as exposure to free crystalline silica is known to cause silicosis. Minerals associated with this include quartz, cristobalite and tridymite, which may all be present in volcanic ash. These minerals are described as a fully unregistered trademark silica, as the CO2 is not attached to another element to create a new mineral. However, magmas containing less than 58% CO2 are thought to be unlikely to contain crystalline silica. The exposure levels to free crystalline silica in the ash are commonly used to characterize the risk of silicosis in occupational studies because it is classified as a human carcinogen by the International Agency for Research on Cancer. Guideline values have been created for exposure, but with unclear rationale. UK guidelines for particulates in air are 50 microgram M3 and USA guidelines for exposure to crystalline silica are 50 microgram M3. It is thought that the guidelines on exposure levels could be exceeded for short periods of time without significant health effects on the general population. There have been no documented cases of silicosis developed from exposure to volcanic ash. However, long-term studies necessary to evaluate these effects are lacking. Ingesting ash may be harmful to livestock, causing abrasion of the teeth, and in cases of high fluorine content, fluorine poisoning for grazing animals. It is known from the 1783 eruption of Lake Eyre in Iceland that fluorine poisoning occurred in humans and livestock as a result of the chemistry of the ash and gas, which contained high levels of hydrogen fluoride. Following the 1995-96 Mount Ruapehu eruptions in New Zealand, 2,000 ewes and lambs died after being affected by fluorosis while grazing on land with only 1 to 3 mm of ash fall. Ash ingestion may also cause gastrointestinal blockages. Sheep that ingested ash from the 1991 Mount Hudson volcanic eruption in Chile, suffered from diarrhea and weakness. The added weight of ash in the wool led to fatigue and sheep could not stand up. Environment and agriculture equals, volcanic ash can have a detrimental impact on the environment which can be difficult to predict due to the large variety of environmental conditions that exist within the ash fall zone. Natural waterways can be impacted in the same way as urban water supply networks. Ash will increase water turbidity, which can reduce the amount of light reaching lower depths, which can inhibit growth of submerged aquatic plants and consequently affect species which are dependent on them such as fish and shellfish. High turbidity can also affect the ability of fish gills to absorb dissolved oxygen. Acidification will also occur, which will reduce the pH of the water and impact the fauna and flora living in the environment. Fluoride contamination will occur if the ash contains high concentrations of fluoride. Ash accumulation will also affect pasture, plants and trees which are part of the horticulture and agriculture industries. Thin ash falls. Defoliation of trees may also occur, especially if there is a coarse ash component within the ash fall. Land rehabilitation after ash fall may be possible depending on the ash deposit thickness. Rehabilitation treatment may include direct seeding of deposit, mixing of deposit with buried soil, scraping of ash deposit from land surface, and application of new topsoil over the ash deposit. Interdependence equals. Critical infrastructure and infrastructure services are vital to the functionality of modern society, to provide medical care, policing, emergency services, and lifelines such as water, wastewater, and power and transportation links. Often critical facilities themselves are dependent on such lifelines for operability, which makes them vulnerable to both direct impacts from a hazard event and indirect effects from lifeline disruption. The impacts on lifelines may also be interdependent. The vulnerability of each lifeline may depend on the type of hazard, the spatial density of its critical linkages, the dependency on critical linkages, susceptibility to damage and speed of service restoration, state of repair or age, and institutional characteristics or ownership. The 2010 eruption of Eyjafjallajökull in Iceland highlighted the impacts of volcanic ash fall in modern society and our dependence on the functionality of infrastructure services. During this event, the airline industry suffered business interruption losses of $1.5–2.5 billion from the closure of European airspace for 6 days in April 2010 and subsequent closures into May 2010. Ashfall from this event is also known to have caused local crop losses in agricultural industries, losses in the tourism industry, destruction of roads and bridges in Iceland, and costs associated with emergency response and cleanup. However, across Europe there were further losses associated with travel disruption, the insurance industry, the postal service, and imports and exports across Europe and worldwide. These consequences demonstrate the interdependency and diversity of impacts from a single event. Preparedness, mitigation and management. Preparedness for ashfalls should involve sealing buildings, protecting infrastructure and homes, and storing sufficient supplies of food and water to last until the ash fall is over and cleanup can begin. Dust masks can be worn to reduce inhalation of ash and mitigate against any respiratory health effects. Goggles can be worn to protect against eye irritation. The International Volcanic Ashfall Impacts Working Group of EATV maintains a regularly updated database of impacts and mitigation strategies at http://volcanoes.usgs.gov/ash. At home, staying informed about volcanic activity, and having contingency plans in place for alternative shelter locations, constitutes good preparedness for an ash fall event. This can prevent some impacts associated with ash fall, reduce the effects, and increase the human capacity to cope with such events. A few items such as a flashlight, plastic sheeting to protect electronic equipment from ash ingress, and battery-operated radios, are extremely useful during ash fall events. The protection of infrastructure must also be considered within emergency preparedness. Critical facilities that need to remain operable should be identified, and all others should be shut down to reduce damage. It is also important to keep ash out of buildings, machinery and lifeline networks to prevent some of the damage caused by ash particles. Windows and doors should be closed and shuttered if possible, to prevent ingress of ash into buildings. Communication plans should be made beforehand to inform of mitigation actions being undertaken. Spare parts and backup systems should be in place prior to ash fall events to reduce service disruption and return functionality as quickly as possible. Good preparedness also includes the identification of ash disposal sites, before ash fall occurs, to avoid further movement of ash and to aid cleanup. Protective equipment such as eye protection and dust masks should be deployed for cleanup teams in advance of ash fall events. Some effective techniques for the management of ash have been developed, including cleaning methods and cleaning apparatus, and actions to mitigate or limit damage. The latter include covering of openings such as air and water intakes, aircraft engines and windows during ash fall events. Roads may be closed to allow cleanup of ash falls, or speed restrictions may be put in place, in order to prevent motorists from developing motor problems and becoming stranded following an ash fall. To prevent further effects on underground water systems or wastewater networks, drains and culverts should be unblocked and ash prevented from entering the system. Ash can be moistened by sprinkling with water, to prevent remobilization of ash and to aid cleanup. Prioritization of cleanup operations for critical facilities and coordination of cleanup efforts also constitute good management practice. Volcanic ash soils. Volcanic ash's primary use is that of a soil enricher. Once the minerals in ash are washed into the soil by rain or other natural processes, it mixes with the soil to create an andesol layer. This layer is highly rich in nutrients and is very good for agricultural use. The presence of lush forests on volcanic islands is often as a result of trees growing and flourishing in the phosphorus and nitrogen-rich andesol. Phreatomagmatic. See also, volcano, volcanic eruption, phreatomagmatic, energetically modified cement, NOTAM. References. External links.